Hi, it's a pleasure for me to give this talk as part of MMC 21, and I'm going to talk to you about how we've been developing a cryo atom probe and specific workflows to push the analytical limits of atom probe tomography. The work was done primarily under the leadership of Lee Stevenson here, and with many colleagues, Seho Kim, who is about to finish his PhD thesis, Ayman El-Tsoka, who is a postdoc in the group funded by the ERC Shine, Isabelle, and Yan Hong. Yan Hong is now back in China, but she really helped us a lot at the beginning of all of this work. And Isabelle is now a scientist at the CA Saclay, and she's also helped us do a lot of the early data processing and acquisition. Olga is an electrochemist who is still, who used to be at MPIE and is now in Helmholtz-Zentrum Berlin and in Erlangen. And she's helped us understand also a number of things that were puzzling to us. And the group is supported by three amazing technicians, Andreas Sturm, Uwe Tedzins, and Christian Bross, helping with different aspects from the atom probe, the FIBs, and the training of the users. And all of this is enabled by the atmosphere and strong support from Professor Rabe, who is the director of the department and of the institute. Conversely, too many microscopy techniques that we might be more used to encountering in atom probe, like in field ion microscopy before atom probe tomography, the specimen itself is the lens, and that's a quote from Erwin Müller, who invented, along with colleagues, I would say, the field ion microscope and then the atom probe. The specimen itself is the image-forming lens, and the imaging ion beams originates from the specimen surface. So in that sense, the preparation of specimens for atom probe is key to getting the data and to understanding the data itself. So how does atom probe actually work? It is underpinned by a process called field evaporation, whereby the atoms sitting on the surface of this needle shaped specimen will be pushed away, dissolved, and ionized successively or concomitantly. There are still debates about this. And then once you've created an ion in an electric field, it gets accelerated away from the surface and is projected. And this overall process is termed field evaporation. And to provoke the departure of the surface atoms, you need fields that are in the range of 1, typically to 5-6 volts per angstrom, so 60 volts per nanometer. A solution to generate fields that are high enough is to use a specimen that is shaped as a sharp needle, like this. And at the end, if we have a radius that is below 100 nanometers, and we apply a high voltage V, the fields that we generate would be in the range of V divided by R, with a constant here that is a field reduction factor to account for the fact that we don't really have a sphere, but we have a needle shape with a spherical cap. And if the voltage is a few thousands of volts and the radius is 100 nanometers or so, the fields can reach fairly easily 10 to the 9, 10 to the 10 volts per meter, which is what we actually need. So how does an atom probe work? We have this sharp needle with a radius of curvature that is below 100 nanometers typically. We cool the specimen down to below 80 Kelvin to avoid surface migration typically. We apply this high voltage. The surface atoms will be progressively transformed into ions, projected away under this very high electric field. The field is distributed all around the needle in the vacuum chamber, and these ions will fly along trajectories that are determined by the distribution of the electrostatic field. And the ions are collected by a position-sensitive detector that records their impact position. And we trigger the departure of these ions either using laser pulses to temporarily increase the temperature and then enable the thermally assisted departure of the ions, or by increasing the field where that lowers the potential barrier bonding the atoms to the surface and facilitating the departure. also in a thermally assisted process, but assisted with at a much lower temperature. We can then measure the time of flight of the ion from the pulse to the detection event, and this is proportional to the mass to charge ratio of the ion. By combining all of this information and using some clever tricks, we can build this three-dimensional point cloud where each point is one ion that was detected and identified. And here you can see the analysis of a grain boundary in silicon that is decorated with a lot of carbon, and the grain boundary is faceted, so we can then locally measure the amount of carbon on different facets, for example, of this faceted grain boundary. Specimens for atom probe are typically now prepared with a focused ion beam, and so we can take the sample and then use the FIB to dig trenches, then use the gas injection system and the macro manipulator to lift out a piece of the material of interest. This can contain, for example, a specific grain boundary or specific interface that was identified through scanning electron microscopy techniques. Then we deposit this onto a support and we weld it with the gas injection system, get the bar free, and we then use a series of annular milling patterns to turn this small piece of material here into a sharp needle. The needle is sharp enough to be electron transparent, so in principle you can always use a transmission electron microscope to image your needle, and you can even do high resolution STEM, for example, in that case with high angle annular dark field, to see the atomic arrangements within these precipitates in a precipitation strengthened steel. And once this needle has been imaged through transmission electron microscopy, we clean it a little bit in the FIB to remove the carbon that has been deposited, and then we can run it in the atom probe and we can correlate the structure to the composition. That's what we get from the atom probe, compositional field. A strong limitation of most microscopy techniques is that the detection of light elements. And this has been a huge issue in the past, and although, for example, hydrogen has been known to embrittle materials for over 150 years, there are still many questions pertaining to how the hydrogen penetrates, where it goes inside of the microstructure, and how it affects the mechanical properties mostly of the material. And it can cause mayhem, bridges failing and pipelines failing, and the cladding of nuclear fuel, for example, breaking down, which is really not exactly what we want. And analyzing these light elements is a frontier of microscopy and macroanalysis. In principle, atom probe offers a possibility to do this, but there are many challenges which I'm going to explain in the coming slides. For example, if we can take a stable hydride, and here is one in titanium that was formed at a grain boundary between two titanium grains, and we can actually retrieve the orientation relationship between the two phases, and we can correlate these compositional analysis with what we would get typically from TEM or EELS, and so we can actually look at combining the information between the two. In that case, this is something that we can do normally with a normal atom probe. Amongst the issues regarding quantification of hydrogen in atom probe is that every atom probe is more or less something looking like this, a stainless steel UHV chamber, ultra high vacuum, so it always contains some degree of hydrogen inside of the chamber. And when we start doing the analysis, there might be hydrogen because the specimen is kept cold, hydrogen will be attracted to the specimen. It can just hop progressively because of the field gradients between the end of the needle and the edges, go towards the ends, get ionized, and get detected. Also, the hydrogen of interest, as I've highlighted before, can be extremely fast diffusing. So even if we manage to put hydrogen in, to detect it, we might have to cool down the specimen and then do cryo-vacuum transfer. There are several efforts across the world to develop cryo transfer infrastructure for atom probe. At Oxford in the UK and in London now it's happening, and also us, for example, here at MPIE or in Sydney. I'm going to give some more details on this in the coming slides. Why do we need this? So if we look back at some of the work that was done in the past few years in the group of Professor Moody at the University of Oxford, you can charge electrolytically a piece of metal shaped as an atom probe specimen, and we can put deuterium in, for example, so we can actually facilitate quantification of the amount of hydrogen and locate it inside of the microstructure. But without the cryo vacuum transfer system, this mobile deuterium will probably migrate out of the needle before we can perform the analysis. If you do the same experiments on the same types of material with the cryo transfer system, you get to detect much more hydrogen or deuterium actually that you've introduced in the sample, which is exactly what you need to do. And this is this H signal that will come from the chamber in parts and also from the specimen, which we will discuss a bit later. And there's this amazing work done at by the Oxford group in parts in Switzerland at Zurich to look at where the deuterium is sitting inside of these carbide strengthened steels. And I invite you to look at the paper. So what we've been putting together in the past few years at MPIE is what we call the LAPLACE project that bridges together a glove box so we can do hydrogen charging under very low moisture environments, a CRYO-FIB, and 2 atom probes and a straight flight path instrument and a refraction fitted instrument, and they're all interconnected by with a cryo transfer suitcase that goes under UHV conditions. All of these getting together in what we call the LAPLACE project. I could tell you why we call it LAPLACE, but this would probably extend beyond the scope of this talk. Also, I probably need more than 20 minutes. And it's all described in this paper published in 2018. The idea was to allow for introduction of specimens into a FIB. The cryo stage is connected to a dewar, which is sitting right here on the side of the FIB, so we can go to about minus 150 degrees, and the needles can be placed in front of the FIB, and we can then do cryo sharpening of the needles and on a coupon, or typically what we would use like a puck here that goes into the atom probe. That's some of the images inside the FIB. So now we've updated this system a little bit, but the idea is the same. So you have a copper block here that's connected to the dewar. It cools down this cryo stage, which is more or less exactly the stage of the leap, the chemical leap, and this is inside of the FIB. And then we can bring our specimens from the suitcase through this intermediate chamber into the FIB, and the intermediate chamber allows us to have exchange from between 2 different pucks actually, and this is also cooled down and under UHV conditions. And then we can mount this same suitcase on the side of the atom probe, and here is directly we go into the buffer, so we maintain the UHV chain. Other solutions go into the atom probe through the load lock up there. So that's what the group at Sydney is using. And we have this fairly large puck that can host another puck, and this we cool down inside of the chamber before and then we stick it in the buffer, and the puck coming out of the suitcase goes directly into this piggyback puck, so it's maintained cold inside of the buffer chamber for a few seconds while we rotate the carousel, pick up this puck with the transfer arm, and then stick this into the analysis chamber. We did a number of tests on samples that were typically sensitive to oxidation, so pure magnesium. And we did a series of tests, for example, preparing the needle at room temperature, stick it in the leap for some time, then do the analysis, and then do the same thing with room temperature fabrication, and then directly run it, or do the cryo preparation and run it immediately. And you can see that the surface of the needle will contain more or less oxygen, and when we do the full cryo protocol, we detect virtually zero oxygen, in this pure magnesium sample. And that was a good indication that if we want to avoid these effects on the surface, even when we do the storage inside of the LEAP, so under UHV conditions, we can have some pickup of oxygen from the surface. But if you do everything fresh and quickly through the cryo protocol for the preparation itself and for the transfer, we end up with much less, a much cleaner surface. One thing that we've also seen is that hydrogen can come from the FIB. This is a known problem in titanium, for example, in titanium alloys. So it's been reported long ago, and the sources of hydrogen can be just the moisture inside of the FIB, or the water during preparation through mechanical polishing or electrochemical polishing, in that case for the preparation of TM lamellar. And when we're doing atom probe preparation at room temperature, very often we would end up with a hydride inside of these needles. And we wanted to find a way to avoid this, because it means that we are introducing hydrogen inside of the specimen during the prep, which is not exactly what we want to do if we want to analyze the hydrogen inside of the needle in the first place. So we started using cryo-fibbing. So we did gallium fib and plasma fibbing at room temperature, and ended up with hydrides. And then we did cryo-plasma fibbing, and we also did cryo-gallium fibbing. And we showed that we didn't find any hydrides in these situations. And through conventional fibbing inside of an alpha-beta titanium alloy, we would end up sometimes with 20% hydrogen in beta. And after cryo-fibbing and room temperature transfer, we would end up with almost no detectable hydrogen above the level of background, which was a very good sign. The next step was to go not only for hydrogen that was not diffusing very fast, but hydrogen that would diffuse more faster. And so we tried a whole range of different workflows, a little bit like what the Oxford group had already done, but through our own infrastructure. And so we wanted to go, for example, from an electropolishing a needle, so not the FIB, and then go through directly into the LEAP, analyze in high voltage pulsing mode or laser mode. We also wanted to see whether we could remove some of the hydrogen from the specimen in the first place by heating in the load lock, and then charging, and then do the analysis, and do this after plunge freezing, sometimes resharpening in the FIB, and then cryo transfer inside of the atom probe. All of this is detailed in a paper in Acta Materialia, and so if you have questions, there might be more details there, or just ping me. But basically what we saw was a whole range of different analysis conditions and results. After heating, we would see a very strong change in this signal from hydrogen without any loading, which indicates that some of the hydrogen that we detect inside of the atom probe actually does not come from the chamber, but comes from the specimen, and we likely introduced it during the electrochemical preparation, because we are removing atoms from the surface in acidic conditions to shape the specimen into a needle, and it results in the presence of atomic hydrogen on the surface that can then penetrate inside of the specimen. So when we want to load with deuterium afterwards, it can cause problems, because most of the sites where the hydrogen could go inside of the structure might already be occupied by hydrogen. So after all of these workflows have been used, high voltage pulsing mode, after heating of the specimen to dissolve some of this hydrogen, we loaded with deuterium, and there we could actually detect some deuterium typically locally segregated at interfaces between these elongated carbides in the pearlitic steel and the ferritic matrix. So we were a bit confident that we could see something quite good. What we also saw was that the signal of deuterium and hydrogen would be affected by the FIB. So even if we do specimen preparation with the FIB in these types of steels, we might be introducing some hydrogen from the moisture inside of the FIB, despite the low vacuum conditions. So all of this was quite encouraging for us. But cryo-fibbing also for other things to be done. So again, if we do a typical lift out, the workflow would look like this. But some low melting point materials, like in that case, it's a gallium-based alloy. When we want to do the lift out, and just because of the illumination with the electron beam or the ion beam, we can actually melt the sample. We're trying to, for example, here deposit a bubble of gallium on a flat surface, and then use an approach that also has been proposed by the Oxford group jointly with the group in Glasgow, to use a plasma FIB and blast a fairly large volume of material to leave just a single needle like this in the middle. And this we could then put into the atom probe and get some data. I'll get back to this in the next few slides. Cryo-FIBing seemed to also make a big difference when we're looking at organic and inorganic materials, for example, with these organic chains seemingly less broken down by the gallium during the preparation of atom probe needles. So we're not exactly sure what's happening there, but we could definitely see a very strong difference in the pattern that we were detecting in the atom probe, and the success rate was also much higher for specimens prepared at low temperature. So I think there's really a lot of opportunities to use cryo-FIBing for many types of materials. This was published in PLOS ONE a couple of years ago as well, and we are now routinely using cryo-FIBing for many other applications. A natural thing that we may want to look at with cryo-FIBing is ice, so water, frozen water basically, and sometimes we ended up with a lot of ice on our needles. And there was some amazing work done at PNNL by Danny Perea and Dan Schreiber, where they were looking at a thin layer of water ice on a glass, and this porous layer in between the two. And so they did lift out with a cryo omniprobe micromanipulator, and they actually had to use the redeposition because you can't really use the gas typically to weld the micromanipulator to the lift out bar, because at minus 170, as soon as you open the gas injection system, the precursor just condensates on the cryo stage, and you can't really weld locally. You just deposit a whole mess. What this indicated to us was that if you have a porous structure on the surface, you can actually trap some of the liquid inside the pores and right above the pores. So we just used the same types of approach on a nanoporous metal. And what we did was just put some water on top, freeze it in liquid nitrogen fairly quickly, and ended up with a needle that was shaped for atom probe. And then we did the full cryo transfer and managed to detect and analyze this entire needle made of ice, and looked at what was happening at the interface in this nanoporous metal, and the distribution of species. For example, here we didn't use just ice water, but a solution of salt water, and we could see that most of the solutes end up trapped in the pores right inside of these the nanopores at the interface between the water and the base metal. So this was really quite encouraging in terms of analyzing solutions for the future, and there's quite a lot of work happening in this space, especially with our friends in Stuttgart. And we also found that some of the silver that came from the dealloying of this the base metal, which is a silver gold alloy, we could see it floating inside of the liquid after the quenching. So again, we could also here analyze some floating pieces of metal in water, which is really quite encouraging. There are many future directions for this work. In principle, we can then look at metals, all range of metals, and hydrogen accumulations near cracks, for example, in alloys, or simply across the matrix. There's a lot of interest in looking at aluminium alloys in the 7000 series. In functional materials, there's a lot of stuff happening that might benefit from cryo vacuum transfer and cryo preparation. So soft metals, soft hard interfaces, catalysts and suspensions in solution. And also this might end up allowing good conditions for looking at biological materials, proteins in their pristine environment. So a lot of potential. And with this, I want to just acknowledge the financial support from the Institute, from the ERC, and from a whole range of different German, mostly German funding sources, the Volkswagen Stiftung and the Alexander von Humboldt Foundation. Thanks a lot for listening.